Thank you very much. I'll be, what I want to talk about today is a problem I've noticed in over a half century of teaching, that students sometimes make ridiculous mistakes. And this is especially true in chemistry. It is also true that I've run into mistakes in professional literature that are just about as bad. So this is something that really needs to be taught starting at the very beginning of chemistry. And once upon a time, we used slide rules. I don't know how many of you remember these things, but they went out of existence about 40 years ago. But they were analog calculators, essentially, good to about 3 figures. And you had to supply the decimal point yourself. So you inherently had to do an estimate of where your answer was going to come out, because the slide rule, unlike a calculator, does not supply a decimal point. So students going back some time at least had some sense of making an estimate. However, a lot of students still try to get by memorizing equations, and without a slide rule, they use a calculator and sometimes come up with ludicrous answers. And in addition, they have to get the idea that they should check their assumptions in doing the problem. I'll give an example, but sometimes discussing a cow, you make the spherical cow assumption, and once in a while that's adequate. Most of the time it is not. So I'm mostly going to talk about student errors, especially of the type: memorize equations, plug in, and write down what the calculator says. Do not think. Now, in exam 1 in the very first year of chemistry, you often ask the student, find the mass of an atom in grams, and let's say the atomic weight is 100. And the student multiplies and gets about the mass of the moon. The moon is big, atoms are small. And the student who just memorizes and doesn't think can make that kind of a mistake. If the student stopped to realize what the numbers meant, what the physical sense of the numbers would be, then they would never make such a mistake. They would realize that they got an answer that was far too big to be an atom by about 45 orders of magnitude. Now, you don't have to be off by 47 orders of magnitude to be really silly. Now, the one kind of approximation that is taught in freshman chemistry and in almost all books is the dissociation of a weak acid or base. But in that case, one writes down the equation for the dissociation constant and then makes the approximation that the initial concentration is much greater than the amount that dissociates, which is correct if the amount of the acid that was added is much greater than the dissociation constant. Then all you have to do is take a square root of the product of initial concentration times dissociation constant, and you've got the right answer. And this is taught in most books. So far, so good. And the student has been introduced to an approximation, and we have a reasonable answer. However, check the assumptions. This is fine as long as the initial concentration is much greater than the dissociation constant. But the assumption is too often implicit. Even if it's pointed out explicitly to the students, no examples are given in which the assumption is violated, so the student never realizes how the assumption is critical. But suppose it is in the other direction. Suppose you have a KD that is greater than the initial concentration of the acid. You use 10 to the minus 4 acid, molar, and the dissociation constant is, let's say, 10 to the minus 3, and you wind up with more acid than you put in initially. So you have a degree of ionization that is greater than 100%. All you can say at that point is, oops, except the student might not notice. Obviously, if you have complete dissociation, the acid should equal the amount that you put in, and that's the most you can actually get. And that is the result you get from the quadratic if you solve it. If any of you are not chemists and have not followed so far, the essential point is that there's a simple equation. It is typically approximated with an assumption. And if the assumption is violated, you get nonsense. All the rest of it was details. Now, I looked at another example here, or I present another example, in which you can make the approximation, and you'll get an answer that's moderately close to the right answer. In this case, 3.7, the correct answer, 3.78. Is 3.7 good enough? Well, it depends on what you're going to do with it. So the student has to think through how much accuracy he or she actually needs. This can be used to introduce the idea of the adequacy of approximations. The topic is a little sophisticated for a first-year course, but students can begin to get used to the idea. This particular example also allows the introduction of limiting cases. In one case, the dissociation constant is much less than the initial concentration. That's where you use the approximation, and it's okay. But it could be the other way around, and you know that the limiting case has to be 100%. You cannot get more than 100% of the acid. So you can even fit them together, and in the occasional case where they're approximately equal, that is the dissociation and the amount added, you could almost fit it on a graph and solve that way. For this particular calculation, that's a very unusual case, but it happens in many other cases. The idea of limiting cases should be familiar to students by the end of the year. And for physics students, it usually is. But for chemistry students, it rarely is. So the student should have been made to understand that there was an assumption involved and should have been instructed to look for it, checking that it was satisfied. And should realize that if no other acids or bases are present, a certain amount of acid cannot produce more than that amount of hydrogen ion. So getting an answer that's greater than you put in, if you're not a chemist, the idea is that you put in something that comes apart, and then you get more of one part than you actually put in to begin with, so that somehow you've generated it out of empty space, which is impossible. It's nonsense. And the student should realize, without doing any calculations, that that is nonsense. So they should learn to rule out physically impossible cases. So every quantitative section of freshman chemistry, which is almost all of it, can be taught with approximations and should be. Here's another example from heat of formation. You're given the heat of formation, you're given an amount that reacts, and find the total heat of the reaction. Well, all right, I mean, again, if you're not a chemist, perhaps you don't get it, but the point is there's a certain amount of energy involved in a reaction. You run a whole lot of this reaction, so you're going to get a whole lot of energy. You're going to get a lot more than you started with. And I wrote it out as would be for a chemist, but if you don't see what's happening, all that is happening is that you're using a lot of the reagent, therefore you get a lot of energy. If you explain that much to the student, already the student is ahead of the game, is going to understand more than the student would otherwise. And in this particular slide, I went through the business of actually making an estimate. You're using 50 times as much of the hydrogen of the reagent So you should get 50 times the energy. And that's basically the whole of this slide. It's not necessary to go through it in detail. The one other point that's made is to make the estimate, we rounded off 92 to 100. And 92 is less than 100. So the final answer should be less than the 5,000 kilojoules that you would get from the estimate. And sure enough, if you actually work it through, it's less. And in fact, you can tell that it should be about that much less. So errors that should have been recognized and should have never been made even appear in the professional literature. I'll give just one example where somebody used an isolated ion. Now, had used what is called the Debye approximation, which requires that you have a solution that's very dilute with lots and lots of ions. These were people who should have known better. I don't have time to go through this, and it's a little bit technical, but the main point is people in a professional approximation and a professional literature made an approximation that was idiotic. Things have to make sense. So the moral of the story is overall that students make errors they should avoid because they do not consider the physical meaning of numbers. For most students, the significance of numerical values of quantities can be taught and must be. Examples of varying degrees of complexity can be found for almost every topic in first-year chemistry. That heat of reaction example that I showed was very trivial, but you can pick more complicated examples. And this also leads to a discussion of errors, which are critical in science, and understanding just how accurate your answer is and how accurate it is with respect to what you actually need. And even experienced professionals sometimes make errors that show they could use a reminder of these points. Thank you very much for listening, and I hope that was clear enough. Thank you.